Okay, so this is a report on some ongoing work with Casey Davis, former PhD student, and Chris Hans, a colleague at Ohio State. We would like to describe the results or a model that we think is very flexible and can produce non-stationary looking output, and hence can be used for the usual set of inference purposes: prediction, calibration, variable selection, and the list goes on and on. So that is the objective. There are 4 sections here, one of which you can read. There's an introduction with some pictures. There's a lot of pictures here. Okay, I'm just trying to give a basic idea. There's some papers that are being written. If somebody wants to know more, that's the place to go. But the first section, just some introductory remarks about stationarity, then a description of the model, and then 2 applications. How does it work when predicting? How does it work for the variable selection problem? So that's it. So again, the objective is to introduce a model. There are a bunch of words here, but the important phrases are Bayesian Composite, meaning sum, and GP, which is since this is going to be a hierarchical model, what we'll see at the top stage will be a Gaussian process. And then we'll look at some examples of prediction, some good points, some good properties of this thing, and some restrictions. And then we'll look at variable selection. So the idea is that this model extends the regression plus GP model. So the regression plus GP model that's rather ubiquitous in spatial statistics and certainly in computer experiments looks as is a sum. It assumes that your little y is a sum or realization of an F transpose beta plus some local perturbations, which can be modeled by a Gaussian process around that mean. Yes,
can I ask,
please ask.
So what is R over rho?
Oh, yeah, this little screwy notation. If you really would know the correlation, let's see here, yeah, if you know the correlation function, then you would use, R would be the notation you'd want to use.
Okay.
If I know the correlation up to a vector of parameters, say rho, then I would use the notation R. So now I'm using this ambiguous notation that says either I know R completely or I know it up to a vector of parameters, and that vector of parameters I'm classifying.
So you said it has a heteroscedastic variance. You mean sigma?
No, it doesn't have a heteroscedastic variance. This has a constant variance. So at any point, the movement up and down is the same, at least stochastically. That's what this is saying. So this model, the standard model, the standard model says constant variance.
Sorry, I guess it's your model.
Well, that's coming.
Sorry.
We're coming. Okay, and if, so ask if you have any questions. If it's too complicated, I'll say we'll talk offline or something, and then we'll try to keep this within reason. Okay, so let's take a look at some examples of what I mean here. The top 4 draws are from the stationary process with a highly correlated, a high correlation between y at each pair of points. They walk more or less in lockstep, at least stochastically, and any draw I take in this process is going to have that same property. Here's 4 of them. If the correlation becomes a little less, then I see more local maxes and mins. If it becomes really small, then I can see something like this. This is in 0. White noise would be sort of 0, and you'd have infinite numbers of ups and downs, infinite numbers of local maxes and mins. So the sigma squared describes how much goes up and down, the correlation, how many local maxes and mins there are, and of course the mean describes the usual thing. So if that's stationary, what are some non-stationary looking y's? Well, here's a couple in 1D. Stay with a 1D input. This, if you look closely at it, you'll see the number of local maxes and mins on the left looks different than on the right. The mean is different on the left than on the right. Well, the amount of up and down this may be different. It's not 100% clear here. But at least 2 things are violations of what you would think of as being stationarity. The right-hand side is perhaps a little simpler, looks like a constant mean. The sigma squared looks like it's varying over x, process variance, and the correlation on the left and the right, I mean, it's pretty up and down. It may be different on the left than on the right. So in any case, that's sort of non-stationarity. Here's a 2D example of non-stationarity. On the outside, you get sort of relatively stochastic constant, and then you get the Himalaya mountains on the center, and so it's clear that something different is happening in the center than on the right. So there are lots of examples of applications which lead to outcomes which, just from a gut point of view, don't look like it could have been produced by a stationary process. So that's the first point. The second point is I just want to motivate, at least my experience, why variable selection is so important. The engineers that I work with are constantly coming up with more and more complicated models. You ran 12 hours last week, it's running 20 hours this week. Why? Because they've included more physics. They've included the possibility of additional variables. So they have, in my case, bioengineering design variables. You want to design a hip, how long should it be? What's the cross section look like, et cetera, et cetera. So those are things you can control. What kind of environment is it running in? What's the loading? Is it normal gait, flat on the surface, up a set of stairs, getting up from a chair, all of which loads let's say, a hip differently. And then there are an increasing pantheon of model variables, things, elasticities. We know the elasticity of cobalt chrome or stainless steel or whatever it happens, titanium, whatever it happens to be, but bone is different. And depending on whether you're male, you're female, how old you are, and so on, your modulus, or let's say the elastic modulus, to say one of multiple things that have to be specified in any sort of finite element code, those can vary. And you can use, well, that's not good. The point is that this can be a useful device if we, for example, have some idea of what the distribution of modulus is for a group of individuals that you want to build a hip for. Then you can use that at the design stage, assuming that we have model variables. And I think this is probably very similar to the numerical analysis group, that the other half of this program, which is looking at solutions to PDEs or sets of PDEs which have boundary conditions which are unknown specifically, but for which distributions can be specified. It's a little like that. Not exactly, but it's a little like that. It's in that spirit. Okay, now let's talk about the model. So what I want to start off with is just recalling that there are some ways, some classical ways in this first instance, of describing outcomes which aren't necessarily stationary looking. So the oldie but goodie, is universal Kriging, which dates back to, I guess, Krieg himself or something, and is the model we started with before. You take a regression plus some deviations from it that represent effects that we can't model precisely using the physics or biology that's available to us, and that is our description of little y, or little y is conceived of as a draw from such a process. So the Gaussian process, you notice I've immediately changed notation. It was r/rho, now it's rho/r. But anyway, this will be one of many perturbations, I'm afraid, in this talk, but just keep you on your toes. And of course, it's no longer sigma squared, but sigma squared z. But anyway, the correlation that's used most often in the universal Kriging literature is so-called Gaussian correlation. If I were to take rho j and represent it as e to the minus theta j, where theta j is positive, then I got a number between 0 and 1. It's oftentimes more convenient just to call that parameter rho j. And there have probably been, I don't know, 3 or 4 other parameterizations of this same model in the literature that attempt to describe the model in terms of parameters which are more easily estimated. I mean, if you have an extreme case here, for example, if you have a rho which is near 1, or data suggests it's near 1, then the estimation procedure, whatever you're using, Dremel or maximum likelihood or something else, cross-validation, it will have a more difficult time estimating the rho than if I use a parameterization which tends to push those extreme values, 0 or 1, back towards the middle. And one simple way of doing that, as we'll see shortly, is to just put a little power up here. Like if I put a 2 or a 4 or a 10 or something up there, then at least it takes the small correlations and pushes them up. If I want the thing, this here, to be estimated to be, I don't know, a fourth or something, and instead I put a rho to a square power or something, then the rho is now a half. I push it toward the center, and a half squared is the quarter that I really wanted for the parameter in this setting. So you use some numerical trickery like that to try to make the estimation process simpler. Otherwise, it can be quite onerous. Okay, so again, the main point here, small rho correspond to more active inputs, and big rho, when rho is 1 in particular, then I don't care what the difference is, you still get a contribution of 1 to the correlation. And smaller rho is you're moving towards white noise, and you get that picture that we saw at the bottom of one of the first sets of slides. So if you use ordinary kriging, which is universal kriging with a constant mean, what happens if we look at the two examples that we started off with, the two 1D examples anyway. The first one, on the left-hand side, it fits, as kriging must, it fits a curve through the data, and it's the red curve. So the blue is the original curve I showed you. But I'll call this function the Ba-Joseph function, or Ba-Joseph-Jiang function. It goes back a number of papers as a test case, the latest of which is, at least the latest one I know of, is a paper by Ba and Joseph. So in any case, we have a red curve, and you can sort of see what's happening here. And the model assumes this is the constant mean model, right? Ordinary kriging. So the model assumes that you're stationary, and what it's trying to do is, in its predictions, is pull this down because it's believing you have something that's walking in locks, and it's stochastically the same for any two sort of intervals, and it wants to be down where this is for points in between here, but then it keeps getting jerked up because of the data. So, there's a lot of uncertainty as to where this real curve is, where the y of x really is here, as measured by these confidence bands. On the right-hand side, we have this damped sine curve, and it also is the upward movement here is just a statement that it's in the data anyway. We see curvatures, of this order of magnitude, and it's not believing that anything as small as this could possibly occur because it's saying, oh, I'm stationary. That's what the model is. So I'm going to fit a stationary curve to it. So that's the red. But also, there's the bands here are a bit, wide, and it's not really quite sure what's going on here. Yeah. Okay, so Ed talked about Bayesian adaptive trees as another way. So our first way is universal kriging of it, trying to tax non-stationary y's. BART is another way. Ed talked all about that, and that talk is online. And gives a very good introduction to this kind of methodology. Tree Gaussian processes are another way of doing this kind of estimation of functions that aren't stationary. And I'll say here, and I'll make a comment at the end, these predictors that use and try to figure out what the tree structure is in the input space, where within a sub-piece of the domain, you're pretty sure this can be fit by maybe a single GP or whatever. They require data, enough data to be able to identify what that tree is, and that will perhaps, at least in some instances, some applications, set it apart from some of the other kriging or even this CGP method we're going to talk about next. Is sort of the amount of data and comparisons that one wants to use it. This is a very attractive idea, but it requires data to figure out what's going on at the input level. Joseph, whose function we've pirated here, introduced something called a composite Gaussian process model. They're non-Bayesian. They estimate all parameters, and the composite here means we're looking at a sum, and the idea is pretty simple. Let's just replace F transpose beta by a process. I mean, if the process is flexible, we should be able to figure out what F transpose beta is, at least if we have parameterized things properly. And in addition, in their most expansive version of this model, they allow for a variance which depends upon the x. So now we have something which appears highly flexible. We have the non-parametric version of F transpose beta. We've got a sigma of x as opposed to sigma, and we've got a ZL, which is a zero mean process. And I'll say more about what the components are here, because we're going to take this and we're going to look at a Bayesian version of it. And then they estimate all the parameters by maximum likelihood. They're able to get away with that because they sigma of x, which is a problem child, they parameterize by a low dimensional function and estimate that function. So it's just like one or two parameters more over and above the correlation parameters and sigma squared for this global process and the local process. Okay, so their method, for example, I'm sorry for the proliferation of colors and scales and whatnot, but this is what happens when you make a talk up from multiple picture sources. Anyway, so the point is, this is that Ba-Joseph function. This is the one they looked at, and their predictor is very accurate. The bands, though, are perhaps deceptively small, because you have to, in all these methods where you use some method of estimation of the parameters, you're picking a particular one based on the data, and then you're saying that the process variance or the variance of the estimated mean is whatever, some formula. And it tends to be a little optimistic, because I'm pretending as though I know what the Gaussian process parameters are. In this case, there are lots of Gaussian process parameters, two processes, the parameters of the sigma squared and whatnot. So the bands here, the width of the bands tends to be optimistic. In terms of this damped sine function, which now looks a whole lot less wavy, or at least has a smaller range than it did before, but you see that, what can we see here? There's the global trend. This is an attempt to plot both the global trend, the YG part, or the expectation of the expectation of ZG, as well as the sum of the ZG plus the local part. And again, it's very accurate prediction. Out here, it is very, very optimistic that it knows what's going on, because these are supposed to be bands above and below the estimated mean. And whether this has any bearing to reality is another sort of issue. Go ahead, Hussein? Yeah, go one second.
Okay.
Yeah.
So to me, in the first picture,
Yeah.
The number of data points are not fair, are not evenly in this input space.
That's true.
So maybe if with this number of data points, if you try with even stationary covariance function, maybe you have kind of similar results. I don't know.
Well, this was the stationary one right here.
Yeah.
Okay,
yes.
Won't recognize it, but it had this property. It was trying to pull everything down, trying to make the prediction look stationary. This second one is not constrained by that requirement, and that's why it doesn't swoop down here between.
Yes, the same ordinary reading here is also ordinary. This
is the sum of two Gaussian processes. I'm using the R function that Sean Ba wrote. They're called CGP if you go to the R archive.
Okay.
I mean, all I was doing was using off-the-shelf software that you can get from the R archive.
So I wanted to say that you called the thing on the right optimistic. You mean pessimistic or
No,
Or are you
optimistic, because I think it's too narrow.
The one on the, why is it?
What
are the
which one
yellow-
are we talking about, top or bottom?
The top one, right.
Yeah,
What
so
is
I
it-
think the
tell me
band
what
should
the
be,
yellow is.
the top, and this is the envelope of the 95% uncertainty bounds produced by the
So isn't
CGP
that,
method.
aren't they obviously too conservative?
I think by picking a particular parameter and pretending as though it was given to you from on high, there's a source of variability that you're not taking account of when you calculate those uncertainty bands. And so they're narrower than they really should be. In
So,
that sense, they're
those
optimistic.
yellow things should be even larger than they are.
Yeah, I think they should be.
Oh, okay.
I mean, a Bayesian analysis is, well, we'll show
Okay.
what the Bayesian fit is. Bayesian would say, wow, not really certain sure that the rho was 0.6 and da, da, da. And, you know,
Okay,
I think it's,
good.
yes.
And the bottom one clearly has problems.
Bottom one is problems, yes. Okay. So now, what are we going to do? Well, the basic idea we like, well, we want to explore in this work what happens if we make this Bayesian, because we didn't like the empiric sort of fit of parameters. And we'll see how to do that. You can, I've put an epsilon here, and I'm going to ignore it for the most part. But anything I do for this model, you can do for this model plus measurement error, and it works just fine. But in the unknown parameters here would be, well, we'll see this set of things. Let's see, the global mean process called YG, local deviation process, YL, and if needed, measurement error. So this model assumes given lambda, given the parameters, the model parameters, everything in sight is mutually independent. The YG has this form. There's a sigma function built into it, and that's what this sigma is. And if I want to calculate the covariance between the global process at x1 and at x2, I take sigma x1, sigma x2 times some omega times g if they're not the same, and if they are the same, it's just omega times sigma x1. Now what's g? G is the correlation function. You can pick your poison here. We were using just what seemed simplest, which was this Gaussian correlation function. And if truth be known, there was some k associated that we put in here. I think it was 10 or 16 or something, because the posterior draws of the rows oftentimes got you into trouble if you didn't try to push them back towards the center. The YL, the local process, which describes deviations above and below, is a mean zero process. This is mean beta zero, the top one, and covariance that looks somewhat similar to this, only there's a 1 minus omega, and the L has its own set of correlation parameters. And I'll ignore the white noise. If we think of this, so this representation sort of harkens back to the original Joseph thought about what this model should look like. But in point of fact, what you have is a sum of things. It's a conditionally given parameters. It's a Gaussian process. The mean is beta zero. The correlation function can be written as a pair of sigmas at x1 and x2 times an omega g plus a 1 minus omega L. And the, let's see here, what I want to say is that without some restriction here, you can get yourself into trouble right away. I mean, for example, if omega is allowed to run over 0 to 1, and I take this to be a quarter of something plus 3/4 of something, and I use the same correlations, I'm going to get the same model as if this were 3/4 and 1/4 or something. So I mean, there's a symmetry about this. So in order for this model to make sense to be identifiable, if you will, there's some restrictions you have to put on the omega, and we typically put restriction on omega that has to be between 1/2 and 1, for example. So right away you see that you have to be careful in the description. To get an idea of what some of these parameters, at least maybe what the sigma squared controls, if we look at some draws from the conditional process, the top level process, for a couple different sigma squared and conditioning on everything else, here we're going to condition on mean zero, and the global process is a higher rho, hence it's smoother than the local process. You get draws, here's 5 draws when the omega is a half, when the omega is 3/4, the omega is 1. And you see the sigma squared, how it controls the range of values you're seeing at the appropriate places specified by the sigma squared as advertised. So this is exactly what we want to happen. So by changing the sigma squared, of course, you get variation in other places. So by changing sigma squared, I get ranges that vary throughout the input space. And by changing the rows, then I'll get global functions that'll be more or less smooth, and local functions which are allowed to go up and down about that mean with greater or lesser frequency. Okay.
Sorry, Tom.
Yes.
Can you just explain again what the difference is between the 2 columns?
Yeah, the 2 columns, everything in sight is conditional given an omega. So now what I want to do is I want to specify some components of the omega as I go down each column. The left-hand column specifies the sigma squared to be this blue function. It also specifies 3 different cases of omega.
Right, so the top plot shows us what sigma squared.
That's correct.
Right.
So there's 5 draws, and this is fixed throughout. Everything else is fixed. And I'm just conditioning, just to give a flavor for what kind of paths or what kind of draws can occur with this kind of process, conditional given lambda, not by taking I mean, of course I could do the whole thing and take a distribution and told you that this was the rho 1, rho g, rho l, and so on. We could see a bunch of things. But here we're just trying to look at the control that the sigma squared basically exerts over the kind of paths you get. And it does as advertised, it controls the range. Okay, so now we make this Bayesian. We put prior on, the omega truncated, this is the half, 1 usually. You don't have to be too careful at the specification stage for the rows. Here, by the way, this pair describes the joint of rho g and rho l to make the G process smoother than the L process. I specify it this way, given whatever the rho g is, like for example, take it to be uniform 1, 1. And then the rho L given rho g is going to have a beta, but I want to truncate it so that its rho value is always going to be smaller than the rho g value. And that's going to force any draw I make to have a smoother YG than YL. So this is, let's see, so there's the rows, and then the function sigma squared. This is where for the moment anyway, we're thinking of this as also coming from a process. Basically, if I take a Gaussian process, which can go up and down and whatnot, above and below 0 even, then I'm going to take, I want to maybe call this W or something. I want to take e to the W to be the sigma squared that I need to specify in order to go forward. And I specify this in stages. I try to make this, the idea of the prior here in practice is to try to make the e to the W close to 1 unless the data tells us it is not close to 1. So in other words, if the variance, the range, didn't depend on what the sigma squared was, it was basically constant throughout, then that would be sort of the stationary sigma squared, then I'd want the sigma squared function to be constant. I want it to be constant. So how do I make it constant? Well, I make it constant by taking choices, at least initial choices of prior, to make this close to 0 and make this close to 1 and so on. Well, not close to 1, but what I want is e to this thing to be close to 1. It means 0. It's a log gamma, or a log normal distribution. Okay, so those are some features of the prior, and let's take a look at how this functions. The usual situation is we're given some training data, TR for training, a test input site, or maybe a vector of those of which prediction is desired. We use MCMC to take a sample from the posterior lambda given y, and then we predict y. Well, here's the main formula. Predictor of y is expectation of y given the data. That's the big E formula, and we condition on the lambda to actually calculate this because the inner expectation has a well-known form. The outer expectation we obtain by doing some Monte Carlo averaging. So this is in a capsule, how we would do this. The drawing of this is actually not quite so simple and requires some detail actually to get this thing to converge, to get the acceptance. Like if you, some of this is Metropolis Hastings. So remember, there's a proposal distribution, and then you do something, and then you either accept the proposal or you don't accept the proposal. And if you don't accept the proposal, you stand put. Well, if there's too many proposals that are declined, then you just sort of stand still all the time. And try to get this thing to work well, at least to have acceptance rates that are in the range 30 to 40%, requires some effort. So in any case, this is from the ith draw, the beta 0. This is a vector of length, well, it's a vector which is 1 by the number of training data points. It's just a correlation of y at each test site with the correlation of y at each of the training data sites. So that's why there's NTR. This is an NTR by NTR matrix. We invert. And this is an NTR by 1 vector. So everything in sight multiplies together and we get a real value quantity. Acting here as though this is, the xt is a single entity, not a vector. And what happens? Well, I want to investigate a couple different cases. They show you a couple different cases. One case is, well, what happens if we apply this in a stationary case? It can be that there's some concern here that the YG and the YL can get confused and we don't know where to put the variation on the YG side or the YL side. So this is a first example. This is a sine function. Sine of 5x is clearly pretty stationary. And the blue function is the YG in this particular case, and it tracks the data. The data are underneath the points here, and there is a red line which describes the sum of the global, this blue, plus the local. And it actually goes, in this particular case, right through the data. So the prediction is spot on. The prediction is spot on. Let's just leave it that way. If I would add some error to this and redo the same experiment, then there's a lot more uncertainty as to what the value is of, or what the certitude is of the prediction. We're not 100% sure we know what the function is. So this is what happens in a stationary case, and more or less, at least for the prior we used, seems to do what we think we want. And I'll show another example illustrating that in a second. Here's this Ba-Joseph-Zhang function, and this to contrast the situation we saw before. The intervals here are considerably wider than what I said were the optimistic intervals that you got by doing just CGP, which fixed a parameter. And this extra variation is due to the fact that we don't know exactly what those parameters are, which are critical in determining what the set of conditional draws are. I mean, we get some wider, let me call them more honest bands at this point about our knowledge of what this function is. So the, I guess that's the main feature here. If you would actually put up the predictions that the stationary one, the stationary process used, or even the CGP, this is going to be closer throughout, it turns out, in terms of predictions. And what happens here? Maybe not too much. The global process is the blue thing, and you can see it's smoother than all the up and down angst of the original curve, the damn sine curve. The predictions, though, are, when I adjust using the YL, are right on. Let's see. This is an interesting example. I did this one because this is this is going to be a case where We don't have a constant mean. We don't have a stationary process. Ordinary accreting wouldn't work here. But there's sort of a global function sitting in the background, and I want to see the extent to which this YG can actually track that. So to get the data, the true function is this curvy, what a line here. And that curvy line was obtained by taking a quadratic and adding some variation above and below it that was generated by looking at a process. So the truth is the bumpy curve. This thing that the regression part is the red curve. And I took 20 points here that are equally spaced on 0 to 10. So it's important to remember 0 to 10 here because that's the point, the range over which I have training data. So we go and we predict, and now I show some random points in 0 to 10, and I predicted at those points. So what happens? Well, as in the previous examples, here's the true curve, and we're spot on with respect to prediction, at least. So take 20 points, predict pretty much any place, I think, within 0 to 10, and you get decent predictions. However, if I predict outside 0 to 10, then everything goes away. It goes bad. So here's 5 points appended on the left and on the right, and you see the predictions go terribly south in this particular case. And the uncertainty bands, of course, are quite wide, and they're an acknowledgement of the fact that the predictor doesn't quite know what the function is. This is heading towards y bar. There's a constant mean for this cap y process. And so when the correlations get close to 0, it's just basically doing y bar, and that's what it's heading towards. So the y bar part this is actually very familiar from anybody that's done kriging. And with a constant mean, you see when you extrapolate the prediction go very badly because it's heading towards y bar and it just doesn't know what to do. So the same thing happens here. The other interesting thing is on the right-hand side. Here I took a look at the posterior mean of the YG, the global process. So I wanted to see the extent to which this YG process actually captured the F transpose beta, which was present in this particular case. Does it do a good job of capturing it? So these are, well, if we focus 0 to 10 and we look at the predictions of the posterior mean of the YG process, it more or less figures out that we had a quadratic sitting there, and we adaptively captured it. And that was sort of the intent of the whole scheme anyway, was to be able to adaptively find F transpose betas. And we are able to find this F transpose beta. But again, if I go outside the 0 to 10 range, things go badly. And so I can't extrapolate very well with this kind of flexible one. I really need data to derive it. So sort of the takeaway lessons might be these. Interpolation is robust. Beware of the Ides of March. Extrapolation is bad. And especially in high D cases, everything is extrapolation. I mean, if you try to, you show your regression students the extrapolation when you show them 2 X's and the data's all up and down the center, and they're making plots of X1 individual and X2 individually, and looks like all of X1, X2 space is covered. It's only the middle though that's covered, and the corners are not covered, and you're extrapolating. And when you have high D, it's easy to extrapolate, and at least many of us work in high D situations. So using some sort of technique to determine whether you're near the center of the data, looking at some Mahalanobis distance or whatever, to try to determine whether a given test point is somehow within the scope of the data, I think is important. Okay, enough about something that's well known, I guess. Let's talk about variable selection. Now, there's a review article in Statistical Science in 2009 that gives a large review of methods for variable selection. And let's take a look, let's see. Okay, let's take a look, or think first of all, the article considers the case mainly for multiple regression. And I've written this sort of in a funny way because I'm thinking already of this being a first stage of a hierarchical Bayesian setup, because most methods for variable selection, or many methods, let me say it that way, many methods in the literature for variable selection in the multiple regression setting are Bayesian in character, and they start with this at a top level. For example, something we'll take a look at in a second is, this is a classic and often used kind of proposal for the Bayesian part, the prior part of the beta distribution. Mitchell and Beauchamp advocate a slab and spike prior. So if I think of putting a spike at 0 for the prior, there's a certain chance, 0.2, that beta 1 is 0, and then it's going to be outside that with some probability and uniformly distributed over, let's say, -1 to +1 or -2 to +2, whatever subject matter experts tell you. And of course, that depends a lot on the range of the x1. I mean, if I've got an x1 that goes from 0 to 1,000 or 0 to 10,000, the beta 1 is likely to be bigger or smaller, I'm sorry, than if it went, x1 goes from 0 to 1 or something. So the prior here has to depend upon the range of the x's, among other things. And then you do some posterior inference concerning each beta. Okay, on the other side, that's the regression, the side of the house. On the other side of the house, in the computer experiments literature, many, not all, but many procedures are based upon the starting, or start with this ordinary Kreeting model. And we recall here that in this ordinary Kreeting model, it's the beta j that tell us how active a particular x is. So if beta j is 1, then the variable is essentially inactive. If beta j is small, it's very active. So that would be the dichotomy, or what we're trying to ferret out in this particular case. So as an example of the latter approach, I'll point to this paper by Linkletter et al. Derek Bingham was here. Crystal Linkletter was Derek's student. And well, anyway, so this came out of her thesis. So the idea was you take training data, you have, suppose there are D inputs to this training data, whatever your favorite D is. And then the proposal is pretty simple-minded and pretty effective too. You add an inert variable, x d plus 1. What it means is you maybe take a random set of x d's, and I add it to the data set. So if there are NTR of these, and I now have another column labeled d plus 1 with n sub tr values. And I regard this function as a function of all d plus 1 inputs. Of course, I've just imposed this d plus 1 on it. It's not a function of xd plus 1 at all. It's just sitting there. It's constant in it. In any case, I proceed as though it were a potential variable. I make posterior draws from the rows given the data, and let's say I make 1,000 draws, and I form the median of this variable I've added. Suppose I had 10 variables, and now this is variable 11, row 11. And then I take the other draws from this process, and I put them off to the side, okay, in a big box, or D big boxes. And then the idea here is this. What I'd like to do is compare the draws from the row J, in particular the median, with the median of row D plus 1. Doing this with a single set of x d plus 1 is problematic because this posterior depends upon what I chose for x d plus 1. So this is never done. So what is done in practice is I go off now and I select a new set of d plus 1 variables. Maybe a new set of random ones, maybe a set of d plus 1 variables which are orthogonal to the column space of the original x variables, whatever. And I go through this whole process of sampling again, getting 1,000 new draws for that second x that I have, and keeping the median for d plus 1 and putting the rest of the rows into their respective boxes. And then I do this a bunch of times, 100 times, 500 times, whatever. So at the end of the day, I've got, let's say, 100 estimated medians of row d plus 1. And what do I do with that? Well, I want to judge whether the other rows have big values or small values relative to that. So maybe I find the upper 10% point of these 100 medians At least that's the proposal in Linkletter et al. And then I take out of their big boxes the 100 times R rows that I've drawn from the various posteriors that I have for the first row and the second row and the third row, and then I examine what the median of that is relative to the median or this upper 10 percentile, and you can make a decision procedure out of it in the sense of if the median for row 1 is smaller than the upper 10% point for the row D plus 1, then okay, that's small, so that's active. If it's not small, then it's big, it's inactive.
Let me ask you, what is rho here?
Rho is the correlation parameter in this Gaussian setup. It's this guy right here.
Okay. So you're adding a variable, and then you're wondering what is the correlation function for that variable?
What is the correlation parameter for each of the rows, and how does that stack up relative to the correlation of a variable I would see that I know doesn't affect the output? This thing I've added, this artificial variable, this reference variable I've added. So all I want to do is examine the rows and ask the question, are they big or small? And I do that by judging them relative to another variable that I've added.
So this is maybe a silly question, but why does xd plus 1 manifest itself in the correlation rho d plus 1, since there's so many rows here?
Well, I'm now thinking of the model as having, first of all, d plus 1 variables. This now product goes from 1 to d plus 1, right? And what I do is I now can form the posterior of this set of rows, the marginal posterior, given the data.
Right.
And I can make draws of this vector of rows, however many, 1,000 of them are. And I start looking at this artificial one, this inactive one, this inert variable. And I say, okay, what kind of rows did the Bayes analysis tell me?
I see. It's just that I think of rho as it's a correlation, so it's a relationship to other things. So rho d is the overall correlation of xd plus 1 with everything else?
Not the overall correlation. I mean, if you look at it, the correlation between y at some x1 and y at some x2 is a product where these hj's are individually the jth component of the first x minus the jth component of the second x squared. If I were to fix an x1, a vector x1 and a vector x2 in such a way that all the components are exactly the same except for one of them, let's say the first one, then the rho 1 to the squared difference between the component for variable x1 and the variable for x2, that would have some interpretation. Okay? So they're all, it's sort of, I don't know, German gemischt or something, I think they'd say. Okay, so what I'm trying to do here is I'm just asking, but what's clear here is that,
I see. It's your last sentence that tells me.
yeah, small rho j are associated with active inputs. That was the key,
Right, from earlier, I remember.
key point.
Sorry, thanks.
No, that's good. And big rho j, conversely, are associated with inactive inputs. Rho j being the most inactive variable I could think of. Okay, so at the end of the day, at the end of this paper, in their examples, Linkletter et al. Show plots that look like this. So this was a 10 variable problem. And I think if you ever read papers in the computer experiments literature, everybody's favorite 8 variable problem is the borehole example, which has, which nobody's eyes are lighting up here. Anyway, it's an 8 variable problem. I think they just added 2 variables that were somehow inert, and then there's an 11th variable. Let me not confuse this. There's an 11th variable. There are 10 variables. They added an 11th variable. The upper 10% point for the 11th variable is this line. It's actually right at 1, showing that variable is indeed inert in the sense that its posterior upper 10% point is 1. And then any median that's below 1 is going to be declared active. So active, 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 active. I can't tell what that is. and these are inactive. So it looks like at least 4, maybe 5 variables are active out of this set. Those would be the active ones. So that's the way this strategy would go. And Moon, not everybody uses correlations. Hedge and Moon, you looked at total sensitivity indices, and let's not do that. So let's look at an extension of the BCGP model that adds on this kind of slab and spike prior that I mentioned before that Mitchell and Beauchamp used. So let's see here. The key point is this. We have sort of the same basic structure we had before, except that now the G and the L have this extra B we have to take account of. And B is a vector of length D, one for each variable. D is the number of variables, number of inputs, and each BI is either 0 or 1. It's a Bernoulli sort of outcome. Okay, so what is the distribution of rho G, let's say G1, given B1? Well, there's 2 possibilities. If the B1 is 1, then this goes away, and it's just the beta we had before. If B1 is 0, then that wipes the second part out, and we've got a spike at 1. So B1 being 0 corresponds to a row which is spiked at 1, hence inactive. And if B1 is 0, that variable has potential for being active to some extent, depending on what the posterior of the beta draw here is going to do for you. And similarly for the row L, it sort of incorporates the same kind of reasoning we had before. It's the same B, and hence these two have to walk in lockstep. Either they're both going to reflect some activity, or they're both going to reflect inactivity. So again, the code is BI is either 0 or 1. It's 1 if the rows are all less than 1 and they have some distribution exactly as previously, and hence they are active. If the BI is 0, then the rows are 1, and hence it's not active. So that's what the idea is. Here's the slab and spike prior. The spike is a spike right at 1. And then there's prior information we put on everything, and some things, of course, you have to specify in pairs and so on. So it's the red portions here indicate what adaptations you have to make to the previous prior that we looked at for the basic BCGP model. Okay, now I want to conclude here by showing a couple examples. First example. This is an example not selected because of its ingenuity, but selected because there's a sequence of coefficients which are increasingly more difficult to detect to see whether the variable is active. And each of these x's lives on 0, 1. So there's no question of the activity of the variable being tied to its scaling in this particular case. So you start off at 0.1, 0.05, and now you're way down here, and can this be detected as being active? So here is, and in fact, there's a couple of zeros that we had 0 times x9 plus 0 times x10. So this is computed for 54 inputs, roughly 5 per dimension. So if I took 5 times 10, I'd get 50. This is a little more than that. And for the life of me, I'm not sure where 54 came from. And anyway, it's a sparse data kind of setting. You have 10 variables, 54 observations, and you could do it with measurement error, which makes it even harder because the measurement error is going to get screwed up with the very low coefficients. So this procedure of doing sampling, adding an 11th column, take posterior draws, look at medians, and then look at the row L and the row G for this X11 is implemented. So what do we have here? The line represents the 10%, upper 10% quantile for the 11th added inner variable. And it's the same on both sides, only this is for the row G and this is for the row L. The point, or the variables that have medians below this line are the ones that are considered active. They have the small rows. And so we see sort of exactly what we had hoped to happen. We see variable 1 with the biggest coefficient is definitely indicated as being important, or active, active, active. I think this is active, and whether this one or not is active, you'd have to get out your microscope and zoom in on. But, it's sort of on the boundary. On the other hand, the local, so these are global variables. So these are the slow-moving or the YG is the process that's smooth, that isn't moving drastically in any input variable. The adaptations, the local deviations from it are quite different. We have at least 5, well, actually exactly 5 variables that are active or seen to be active in order to make local adjustments above and below the YG in this particular case. So you get sort of information about both parts of the process with this kind of an analysis. Okay, so I want to do one sort of quote unquote real data example. This is a data that describes wing weight of a light aircraft, and there are 10 inputs to the wing weight calculation. So, and this is important if you're designing an airplane. Some of these are sort of obvious, and we understand the wing area, paint, the weight of the paint on the wing, okay, it weights it down, and so on and so forth. Some of these, the rest of these, the weight of the fuel, that's clearly, seems like it's pretty important. But the aspect ratio, these are all geometry variables. And if you're an aerospace engineer, you'd know what those mean. I'm not sure quite what they mean. The chord is like a line that goes from the end of the wing back to the place where it attaches to the fuselage and so forth and so on. In any case, we have geometry variables and we have sort of intuitive variables, if you will. And if you were just to make a plot of these things, as any data analyst would, you plot your data step 1, right? You would see this kind of behavior, and you'd say, well, this looks like it's doing something, and maybe this is doing something, and this doesn't look like it's doing too much, and this doesn't look like it's doing too much. And then you go off and you try to do this variable selection, okay, to see in a more orderly fashion, if you will, a statistically justifiable fashion, who's really affecting the wing weight. And in fact, when you take a look at the variables, you see this one, this one, this one, this one. There are 5 variables that affect or active in determining wing weight. And the wing area, okay, we like that. This geometry variable, gross weight, paint weight. Okay, so I mean, it's believable. Of course, without having talked to anybody that knows anything about wings, seemed reasonable. But that's what the data are telling us. Let's leave it at that. And similarly, the local process has roughly actually the same set of variables plus an additional couple geometry variables. This TC, the airfoil thickness to chord ratio, I think it has to do with the amount of curvature in the wing and whatnot in describing it in technical terms. So we have the same variables plus a couple other geometry variables appear important in the to describe wing weight in this particular case. Okay, so here's the end. This model is flexible and can produce many non-stationary shapes. Prediction is accurate when interpolating, but need not be so when extrapolating. And in particular, this kind of a model reverts to the average output when predicting at a test site from the training data. Extrapolation can be difficult to recognize. Mantra again and again here. The design of locations of the simulator runs is critical for this or any GP-based method to work well. I mean, if you don't have the data spread out, when you have a highly flexible model, the model can do anything outside of where the data are, and you need to have a space-filling set of inputs. And you need to know where you want to predict in particular. Okay, there's some general comments I want to make. So this is sort of summary part, and the discussion part, I guess, is this. I have long been interested in gray box prediction. Ed talked about gray box prediction, where you know that Y is monotone in a given X. So, I mean, if we think of codes being black box and know nothing, gray boxes, I know something. Maybe not everything. So it's between knowing Y and knowing something. It's monotone, it's unimodal, it's whatever it happens to be. There are, Peter Chan at Wisconsin is also looking at gray box kinds of codes and trying to build into it other kinds of symmetry, other kinds of known relationships between the Y and the X's. But there's no gray box anything in this model. And I think for it to be truly useful, it needs to be gray box, at least with respect to some properties. The amount of data, this sort of goes back to the beginning. The amount of data you need to do this, if we wanted to compare this method with BART or any other method, is really critical here. And I think you can get by with less data if you're interpolating, maybe with this kind of method than with BART, but I may be, all wet. And so I think that sort of is certainly a critical limiting factor. I know many people I work with tell me, well, I can give you 5 runs because the code takes 24 hours to run. Great. So think hard about where you're going to ask them to run the code, right? I think we're all faced with that kind of a situation. Okay, another important point. Everything I've said about deterministic data, I've hinted at. Also, at least as far as the kind of procedures we're looking at, works if you have data that contains measurement error. So if I want to do variable selection with measurement error, I need, of course, a bigger VCGP with measurement error, and you can do that. And Casey has implemented some of that in MATLAB code. Last idea, and I think this is important. The variable selection procedure, as I described it, adds an inner variable. That's probably not what we really want to do. What makes more sense is to add a low activity variable, a variable that isn't influencing y very much. I mean, it's very seldom you're in a situation where an x does nothing to the y, but it may not do much to the y. So what we'd like to compare are the rows for a given low activity variable with the rows corresponding to the data that we really have. One way of doing that is to add something that looks like this, some beta star times xd plus 1, and there probably should be another factor in here, because if the range of values of the function is 0 to 100, then what constitutes a big effect may be quite different than if it's 0 to 10,000 or something. So I'd like to look at maybe some fraction of the range of the y data, maybe 10%, and then add a coefficient times that range times an xd plus 1 to the y. Actually perturb the y and change the y so that we're analyzing changed y data. How would I analyze or change or choose the beta star? One thing that we've done is the following. We've assumed available some sort of test bed of functions that represent applications of the type that we're interested in. And for that set of applications, we try to choose the beta star to be big enough that to do 2 tasks in medical terms, to be both have high specificity and high sensitivity. They have high chance of detecting active variables, and they have high chance of rejecting non-active variables. In medicine, everything should be high, sensitivity and specificity, right? They both got to be high. So here we want, the 2 good things are high chance of detecting things which are really active, high chance of rejecting things which are truly inactive. And you can tune with a test bed and some effort the beta star that you add on to perturb your y to have those kind of properties. And I think that's a good idea to implement in these variable selection schemes. Hae-Jung did this in the paper that we wrote that appeared in Technometrics for a test bed. Okay, that's it.
Okay, any questions?
So I sort of a comment and maybe a
Maybe we
question.
should,
Yeah.